I expect that many of you are familiar with mediating variables. Mediator is a variable that's intermediate in a causal sequence relating an independent variable to a dependent variable. There's lots of examples. For example, tobacco prevention programs seek to change social norms, which reduce tobacco use. The mediator is in bold print here. Neglect, abuse in childhood is associated with impaired threat appraisal, which leads to aggressive behavior in adolescence. Screening programs increases identification of cancer, which reduces cancer deaths. Wellbutrin, for example, increases participant self-efficacy to quit, which is associated with 1 month abstinence from tobacco. And maybe you could take a few seconds now to think of an example perhaps that that's most dear to you. Here's a diagram of the single mediator model, and most of this talk I'll focus on the single mediator model. This is a diagram that we're used to seeing in SEM, although I don't have the residual variances here, where variables are represented as boxes, and we have directed arrows, and the arrows indicate the direction of causality. We have X causes M and M causes Y, but then there's still a direct effect of X on Y represented by C prime. The same diagram specified using a directed acyclic graph, or DAG, and this comes out of the modern causal inference literature. Looks the same, except we have dots for variables instead of boxes. But again, we have X to M to Y, and then there's still this direct effect of X to Y that's not through M. Here are some definitions of mediation. It's a chain whereby an independent variable causes the mediator, which in turn causes the outcome. And then my favorite definition is from an epidemiology textbook. I'm sorry, epidemiology definition, that it's a variable that occurs in a causal pathway from an independent variable to a dependent variable. It causes variation in the dependent variable, and itself is caused to vary by the independent variable. And this is the issue with mediation analysis in general, is that the mediator is both a dependent variable in one equation and an independent variable in another equation. And this creates some challenges in trying to come to causal conclusions from a mediation analysis. Most of statistics focuses on two variable effects. With two variables, let's call them X and Y. There's a limited number of relationships. X could cause Y, Y could cause X, X and Y could be reciprocally related. We have names for these two variable effects: correlation coefficient, covariance, regression coefficient, odds ratio, or mean difference. Mediation is an example of a third variable effect. With three variables, there's more options, but it's still limited: X to M to Y, X to Y to M, Y to X to M, for example. And there's special names for these third variable effects. There's a confounder effect, a mediator effect, and a collider effect. Of course, the mediator effect is what we'll focus on today, but these other types will come up. With four variables, there's lots of possible relations. And with five variables, there's so many possible relations, maybe it's better to just go home and take a nap rather than try to figure it all out. But we still do that because we know in the real world, lots of variables are related to an outcome that you're interested in. And usually what researchers do is they focus on smaller versions of the model, typically a mediation model or maybe a confounder model. Here are the three possible third variable effects. With three variables, there's a mediator, also known as a chain, where I've represented T as the third variable. So X to T to Y is a mediator, and confounder is a third variable that's related to X and Y. So we have T causing X and Y. And then less attention has been applied to colliders, but they're important. That's a situation where X and Y cause the collider. So mediation has been called a chain, collider has been called a fork, and a collider, confounder has been called a fork, and a collider is like an inverted fork. And with real data, of course, there's usually non-zero relationships between X and Y. So this slide, I've just added the X to Y relationship. And so starting with mediator, that's the focus of the talk. It's a variable that's intermediate in a causal process between X and Y. A confounder is a variable that causes X and Y. And if you fail to include it in the analysis, you'll get an incorrect estimate of the relation between X and Y. And then finally, a collider is a variable that's caused by X and Y. And in an opposite way to a confounder, we should not adjust for a collider, because if we adjust for a collider, we'll get the incorrect relationship between X and Y. In this talk, focuses on mediation, but confounding will come up. In fact, confounding seems to be a central theme in the modern causal inference approaches as ways to deal with confounding, and colliders will come up less often. Mediation is important. I guess you're here today, so you understand why mediation is important. But central questions in many fields are about mediating processes. It's important for basic research on mechanisms of effects, but it's really critical for applied research, like the development and evaluation of prevention and treatment programs, where mediation methods can help identify the critical ingredients leading to more efficient and less expensive interventions. And this is how I started to, or why I became interested in mediation analysis back in the mid or late 80s, when I was working at the USC Institute for Prevention Research, and we were trying to develop intervention studies. And it seemed like there ought to be a more scientific way to develop these interventions rather than sort of coming up with some good ideas and just doing your best. And mediation was a framework to develop these programs and also evaluate them. And of course, mediation is great fun because it has lots of statistical and mathematical issues. Remember, it's just adding a third variable has all these different possibilities that are worth investigating. And I would argue that the mediation model is, if not the first, one of the first type of SEM models to investigate. So if we could solve some of these problems with mediation, ideally they would extend to more complicated models as well. The stimulus organism response theory is ubiquitous in psychology and other areas. The idea is that there's a stimulus and a response, and the organism mediates the effect of the stimulus to the response. So for example, let's say I asked you to multiply 24 and 16. That would be the stimulus. Your answer, 384, would be the response. And the mediator would be the processes that went inside your head to do that calculation. I like the SOR model because it shows the challenges. Here's a diagram where I've just replaced the variables with the variables from SOR models. We have a stimulus X, response Y, and then we have these mental and other processes that occur between X and Y that translate the stimulus to the response. The SOR model shows the challenges of mediation analysis. Usually that mediation process is unobservable. It's something that, at least for humans, goes on inside someone's head. You could view mediation as entirely a measurement problem, that we improve or we gain knowledge about mediators as we are better able to measure the properties of that unobservable process. The process can operate at many different levels. It could be at school level, individual level, cell level, atom level, teams, states, for example. The mediating processes can happen simultaneously across these different levels. And then the mediating process may be part of a longer chain. Typically, it's the researcher's job to pick the part of the chain for investigation.